I am Mr. Ish and I welcome you all to this video. We're discussing here by means of a single question molar volume. What is the molar volume? It's a concept that you need to understand. It relates any ideal gas as having a volume of 22.4 liters under standard temperature and pressure, 1 atmosphere and 0 degrees Celsius, which is basically 273 Kelvin. An ideal gas, or a gas you assume to be ideal gas, will have a volume of 22.4 liters, 1 mole of that gas. And that would be another item you need to remember. 1 mole of that gas would occupy 22.5 liters. This serves as a very good stoichiometric factor with regards to determining the number of atoms or molecules of a given gas under ideal gas conditions if you're utilizing this. With this factor to give you the Avogadro's number coming into play, and I want to show you that by means of a good question. Our question is this: we have 50 liters of nitrogen trichloride which decomposes fully under STP. We have to find the number of molecules of the products that are generated. We have 50 liters nitrogen trichloride decomposing fully, meaning the reaction is in one direction under STP, and we have to determine what the products are along with the respective number of those molecules. Your reaction is this: nitrogen trichloride will decompose fully in a single direction to molecular nitrogen and molecular chlorine. You have to balance this. If you put a 2 over here, you balance the nitrogen, but you put a 3 over here and you've balanced everything. We have to remember this. We should start by determining the mole of this using the molar volume constant. The 22.4 liters per mole is the molar volume, the molar volume constant of a gas or an ideal gas under STP. When we're looking here at NCl3, we have 50 liters of NCl3 times 1 mole of NCl3, which occupies 22.4 liters, and this will give me the number of moles of NCl3. And look, these cancel out, and this should be here NCl3. It would cancel out, and you would be left with only with the mole of NCl3. 50 divided by 22.4, we can do that on the calculator. 50 divided by 22.4, we have 2.232 moles NCl3. Now we can easily determine everything we need. We can do it the long way, we can do it the short way. I will do everything the long way so there are no shortcuts. Right here, looking at nitrogen, we're starting here with 2.232 moles NCl3. We'll multiply it by 1 mole of nitrogen. Why 1 mole of molecular nitrogen? Because 1 is generated per 2 moles NCl3 times. Now bring in the Avogadro's number. 6.022 times 10 to the 23 molecules of nitrogen, molecular nitrogen per 1 mole of N2. Now if everything is done properly, things will cancel out. You have this, you have this, you have that molecules of nitrogen remain, and you just have to do this computation and it'll lead you to your answer for this specific product. You have 2.232 moles times 1 divided by 2 times the Avogadro's number, 6.02 exponent 23, and that tells you 6.72 times 10 to the 23. That right there will represent the number of molecules of nitrogen. 6.72 times 10 to the 23, and we'll write it molecules nitrogen. Now the short way is this. You know each mole of this corresponds to 3 moles of this, so you'd really multiply this with 3 and it'll give you the item here for chlorine. That would be your shortcut over here, because each mole of this corresponds to 3 based on your balanced reaction, and that's what you can do. But that right there is a shortcut. If you have to do things the long way, I'll show you that. Now let me show you for chlorine. We bring chlorine over here. For chlorine, we're going to start again with 2.232 moles of NCl3. We'll multiply this by 3 moles. And you have 3 moles of chlorine diatomic being generated from each 2 moles of nitrogen trichloride. Then each mole of this chlorine gas, molecule or atom, it doesn't matter. This chlorine diatomic chlorine serves as a single entity with regards to the calculation, just as a single atom of chlorine would. 6.022 times 10 to the 23 molecules. Hence I'm using the word here molecules of chlorine divided by 1 mole of chlorine diatomic. That will cancel out, that will cancel out, that cancels out. You're left with just this, and we'll calculate it and we'll place the answer for you right over there. It's not going to be a difficult number by any means. 2.232 times 3 divided by 2 times 6.022 exponent 23. I'm getting 2.02 times 10 to the 24. 2.02 times 10 to the 24. 2.02 times 10 to the 24, that refers right here to my molecules of chlorine. If I were to divide this value right over here with this value right here, we'll have exactly this factor 3 come out, and I will show you. It will confirm the shortcut you could have taken. Divided by 6.72 exponent 23, which is this, the molecules of nitrogen, and you have 3, and we're good. So basically you're seeing how the molar volume here, the concept of the molar volume, plays very much as a stoichiometric factor. You can do this, 22.4 liters per mole, and you can utilize this to determine the number of moles. Once you've determined the number of moles, you can always use this. The Avogadro's number is the number of atoms or molecules of anything per 1 mole of that item that you're evaluating. But the items are over here for you. There will be more molecules of chlorine than there will be molecules of nitrogen, simply based on the coefficients you see over here. 2 of these decompose to give you 1 of this and 3 of that. Hence, this will always be 3 times the number of molecules in that. And that's it. Thank you for watching. Have a good day.